So thank you. As everybody starts to kind of file into this, welcome to our second webinar of the year. We got another good set of presenters that are going to be talking about using new technologies to help improve your existing equipment performance. But before we get to the good stuff, I'm going to introduce, set the table, do some housekeeping items related for the DSUA. So my name is Mitch Lund. You guys probably recognize me from the last webinar. I'm actually the host today. Jerry Hunt, our president of DSUA, couldn't make it today. So you got me today, so buckle up. So real quick, for those of you that haven't joined a webinar yet, what is DSUA? We are a nonprofit organization that's been around since 2008. Our objective is to promote the collaboration and innovation of dry scrubbing technologies. That's SDA, that's CDS, that's DSI, anything that's using dry scrubbing to remove acid gases, right? And we also are used as a venue for networking, new people in the industry, old people in the industry, and everyone in between. Along those lines, we usually have a once-a-year conference, and as some of you may be aware, we are in the middle of a pandemic, and unfortunately, although the light's at the end of the tunnel, right, we have decided as a group to cancel our in-person conference in 2021 due to the pandemic, and certainly, hopefully next year we'll be able to see each other again. In the meantime, we're going to keep doing these webinars to stay connected and share new ideas. So these webinars are going to be recorded. So if you can't join live, they're going to be uploaded to YouTube. So you'll be able to check back and reference if you get distracted or whatnot, but they'll be around. I also want to highlight for the audience there for questions. We're going to do questions and answers like we did last time, which in the portal, there should be a Q&A box that you can click on that, you type it in, and then the questions will go to myself, and our moderator today is Guisu Liu. We'll be able to filter those questions and ask the hosts live, or the presenters live, the questions you're submitting. So please do that to stay engaged in the presentation. I will say we're doing a little something special for this webinar, something new, which is we're offering up a raffle from a few of our sponsors. This episode sponsors that are doing the raffle are National Filter Media and Lwass North America. All the end users that are attending this webinar are going to be automatically entered into the raffle. And if you're selected, we're going to put you in touch with the respective sponsor to coordinate details so that you can receive your goodies, your swag. Before I get to introducing our moderator today, I wanted to take a moment to acknowledge and thank the webinar sponsors for the DSUA. I mentioned we're a nonprofit. If we don't have our sponsors, we're non-functioning nonprofit. So they're important to us to keep all these webinars going. If the audience would like to learn more about any of the sponsors or get in touch with them, you can reach out to them through to the DSA through the webinar, you can reach out to them to DSUA through our website, or go to the homepage, and if you click on the sponsor logos, you can get to all of their websites. So I'm going to take a moment to acknowledge them. Just 1 minute. Got to get my notes ready, my presentation correct here. Share screen. Okay. So hopefully you guys can see my screen. You should see some sponsors here. So the first sponsor we want to acknowledge is Reaction Analytics Solutions Corporation, or RAS. They specialize in engineering solutions using CFD modeling. Their founder is Dr. Guisu Liu, who is going to be our moderator today. Guisu has spent over 2 decades in fuel combustion and emission control technologies, and he's developed over 100 CFD models throughout his career. So he's very experienced. Whether it's front-end combustion or back-end flue gas treatment, RAS can support from modeling the process chemistry to optimizing and interfacing of chemicals and exhaust gases. Recently, RAS has used CFD for DSI and ACI applications to optimize system performance, which is why Guisu is a supporter of the DSUA. Our next sponsor we want to acknowledge is primex process specialists. They actually presented last week as well. You guys might remember Stewart Nicholson, who is actually the former president of DSUA before he handed the reins to Jerry. What primex does is they provide comprehensive help for SDA, CDS, and DSI users to optimize scrubbing performances and their operations. Primex has over 20 years of customer success, demonstrated through a unique combination of knowledge, technology, and patience, which is important in any equipment optimization project. So a big thanks to Primex for being a sponsor for us. And lastly, we also want to acknowledge and thank Lhoist North America. Lhoist is a subsidiary of the Lhoist Group based out of Europe. They are a global limestone, quicklime, hydrated lime, and silicate minerals company. They produce enhanced hydrated lime products that are engineered to optimize dry scrubbing solutions, which are used to control acid gas emissions in both power plants and industrial applications. So those are the sponsors we're going to thank before our first presentation. And what I'm going to do next is I'm going to introduce Dr. Guisu Liu to the mix. I'm going to stop sharing there. So I've given a little background on Guisu so far, but Dr. Liu has gotten his bachelor's and master's degree of engineering in China. He has a PhD in chemical engineering from Australia. Since Guisu's moved to the United States in 2001, he's been working in the power and emission control industry. He has strong expertise in combustion and pollutant chemistry and CFD modeling, as I mentioned, as part of the sponsor announcements. He founded RAS in 2017 to provide CFD-based analytical services with a focus on chemistry and how to maximize the mixing between chemicals and flue gas for best utilization efficiencies. He's published 6 patents, over 130 technical papers. In his spare time, he spends time with his family, and he used to play basketball, but now he's switched to running for fun. And I tell him that it's because he kept breaking too many rims from dunking, so that's why he had to switch. But anyway, having said that, Dr. Liu, take it away.
Thank you, Mitch. Again, I'm a moderator today, so today we have 2 presentations. Both presentations are discussing how to optimize the SDA system by addressing mechanical and chemical aspects of the system, which is kind of nice. So just a reminder to our audience, if you have any questions, you can submit your questions in the platform, and we will have a presenter to answer your questions during the presentation or at the end of the presentation. So our first speaker today is Stewart McKenzie from Lechler and Scott Sloniker from JEA. So Stewart, his education combines a strong academic background with a business acumen, which leverage MBA and a Bachelor of Science in Chemical Engineering to effect solutions for customers and partners. Stewart has developed a broad experience through his career. He has experience in cement, chemicals, power, materials, mining, paints and coating, and alternative fuel industries over his 30+ year career. Stewart has worked for large corporations, including FMC, DSM, and Mitsubishi, and a couple of startup companies. He has deeply involved in the cement and power industries since joining Lechler in 2014. His current role takes him across the southern tier and mountain states, as well as Texas and California. Stewart is also an advisor to the Dry Scrubber Users Association. So now Stewart tell us what your presentation, and you have a 25 minutes of a presentation followed by 10 minutes questions. Stewart.
Okay. Did my presentation come up? Can you see that? No?
That's perfect.
Okay.
We're live.
All right. Good morning, ladies and gentlemen. I hope you're doing well today. I want to first introduce my co-speaker, my colleague, and my partner in crime, Scott Sloniker, who, when I was working with him, was the AQCSC supervisor, but now is more of a operating engineer. Scott, you want to say hi?
Hi, everyone. How are you doing today?
Very good.
Yeah.
Well, what we're going to do today, we're going to tag team this. I'm going to introduce some of the slides and maybe talk about some of the technical nuances of nozzles, but I'm going to leave most of this open to Scott, and because he's the one who lived with it and really had the most to gain and to lose from it. So with that said, I'll go to the first one. Scott?
Yeah. Oh, I'm sorry. So as Stewart mentioned, I lived with it day by day here at Northside. Our original spray nozzles were just insufficient. The SO2 capture rate was not where we needed it. They were maintenance unfriendly, a daily process with those. And we've got a little history of the plant. We've got 2 CFBs. They're 310 megawatts each. Of course, each one of them has a SDA. They're sister units, if you will, although you know how that is. They might be twins, but they're nothing alike. So, let's proceed, if you would, Stewart. This is basically a flow diagram of the flue gas. A little different than our plant. It's not quite exact, but obviously it leaves the boiler, passes through the, we have cyclone separators. The heavies return back to the boiler for recombustion, if you will. The light particulates, which are fly ash, they pass through the heat recovery area and on back to our SDA, where we spray it to remove the last bit of SO2. Our SDA project involves 16 lances per unit, both units. The original spray heads we had, we would get wet bottoms of the SDA up to twice per week, which resulted in men having to actually physically rod it out. Capture rates were low. Our compressed air consumption was previously at about 295 CFM per nozzle. With the Lechler nozzles, that's dropped to an average of 230 CFM, which has allowed us to remove an atomizing air compressor from service with up to 150K a year in savings. Limestone usage, we've reduced our limestone usage approximately by half, well, by a ton at least per hour, which is great compared to the previous nozzles. And of course, the maintenance costs, which we'll get into some details on the following slides.
Hey, Stewart.
Yes, sir.
Maybe Scott. So I have just a quick question. So when wet bottom happened, what is the impact on the operations?
Okay, it of course, like anything, depends on the severity. If it was a wet bottom that merely plugged a small portion that leads to the conveyors to take out the remaining solids to an emergency pit. It could usually be cleared out without reduction in megawatt load. We did have a few occasions, and actually once or twice a year, we'd have to reduce load a little bit, or at least maintain load without moving load. And that would be due to a wet bottom that was so severe, it could take a shift or two or a day and a half to clear. Excuse me just a minute. Oh, I thought I was going to sneeze. Sure, it'll come in a moment. So that was what would occur with the wet bottoms. Not often did it cause us to have a reduction in load, but it did too often.
So when I first talked to Scott, I visited the plant and asked them what was going on, what were the problems and everything. And this is what they showed me. Scott, if you want to talk about that slide.
It is. So the top left is obviously a new cluster head of which was TurboTac. Very nice looking example of how they started out. Unfortunately, they required us to maintain them daily. They had to be cleaned every day due to loss of performance. Our cleaning was very rough on them, as you can see. And they just didn't last that long, unfortunately. The bottom right corner is the most severe, where the actual nozzle insert was compromised and it caused washing of the head, basically a complete failure. So it was, unfortunately, they worked good for about 20 hours. And then, within a day, they required cleaning. So not the best for us, by no means.
Now, Scott, there's a white coating on the face of that nozzle head. You want to explain what that's for?
Yeah, that is oh geez, I've lost the term for it. But basically, it's plastic. It's Teflon type cover that went over it to reduce bearding and buildup. Unfortunately, it worked a little bit, but not really that well. So between the internal fouling and the external buildup or bearding, if you would call it, like I said, the performance dropped off within a 24-hour period. So. There you go. It's a perfect example of it. Bearding. And then if you notice the top center nozzle, a little off center, that's actually an example of pluggage. You notice how all the other nozzles are white on the inside. That's the ceramic. The top center one is gray, and that's plugged with slurry, which is, yeah, that's correct.
And Scott, this is Mitch. So
Yes, sir.
this slide combined with the last slide, obviously these nozzles look like they're in pretty rough shape. I guess two questions. First off, the nozzles on the previous slide, how long did you say they were in service? And then the second question is, do you know what caused the degree of scaling so quickly?
Well, the let's say the I'll accept the new one there. That could be 6 or 8 months old. So that didn't happen within the 24, 48 hours by no means. So that some of it was acid attack due to our cleaning method, because we had to clean them aggressively because we were cleaning them every day. And others, it was just internal erosion. Separate from our cleaning methods. Now, as far as the buildup, I'm not really sure of the cause of that. Just the environment did not suit this application. That would be my best guess. And of course, once a nozzle would plug internally, the performance of that head is completely interrupted.
Gotcha. I appreciate that.
Well,
Sorry for interrupting. Keep going.
so example of the Lechler cluster head nozzles. As you can see, this is a 48-hour example compared to the TurboTax on the previous slides. The bearding is minimal, no pluggage, no performance issues, so no cleaning. It hadn't been cleaned in 48 hours. So basically, we pulled it as an example. There's another one. That's 6 days in service during our test phase with the Lechlers. You can see the extensive bearding, well, more extensive, but 6 days into it, but it didn't affect the performance. So we carried on. We actually undisturbed, placed that right back in the access port for the SDA, placed it back in service.
So with respect to the equipment selection that they made, we really started this design many, many years before this project actually took hold for us. And this was probably the third or fourth evolution of our design. It is twin fluid, meaning it is air atomized. It's a 4-tip cluster head is what we call that whole thing. And then we had tungsten carbide inserts in it because tungsten carbide is excellent for wet abrasion resistance. And so those are separate pieces that go in there. And of course, this is what we call a Laval size style nozzle, primarily for maximum minimum free passage. Whenever you're spraying slurries or high solids materials, you don't want a bunch of really tight passages. You want them as open and as large as possible. The Laval is our style that typically gives that. Also, being in the very conservative power industry, despite all of our assurances, we offered them a trial for up to 90 days. That was to put them in, run them, and if they didn't like them and they didn't like the way they performed, we could continue to work on them and improve them, or they could just return them and say, I've had enough. That's how confident Lechler was in these particular setup in this particular nozzle. At the time, I was probably only a year into my tenure with Lechler, so I was pretty ecstatic to hear all the stuff coming up. But and then when I saw the confidence that Lechler put in their equipment, I was pretty jazzed. Additionally, one of the things they wanted were power references. And we have 2 other very dominant power companies, Dominion and Dynergy, who both have incorporated this exact kind of head into their operation. And they were more than happy to call, make comments and things like that. And I think, Scott, didn't you have some personal interaction with them?
We did. Dynergy, actually, 2 representatives flew down. They brought a sample with them of a tungsten carbide insert that had been in use for over a year at a coal power plant, which is much more abrasive than coal and petcoke mix like we do at Northside. Virtually, you couldn't tell it from a new one, in essence. So yeah, it was a good meeting, which furthered our leaning towards your product. As Stewart mentioned, the 90-day trial, we were limited to how much we could test the product online without purchasing. And so once I approached Lechler, Stewart in particular, they were more than willing to work with us to ensure we were happy with the product before purchasing in full. So it was a wonderful experience. Yeah.
Well,
Hey,
thank you.
Scott, before you move on, I have a question from the audience. The question was, Was there a change in fuel, like a coke to coal or coal to coke blend during a nozzle evaluation?
Not that I recall. We typically have always burned a mixture of coal and coke, whether it be 60/40 or 80/20 or 50/50. So there might have been a small shift. I'd have to reference my testing notes, but anytime there was a shift, I would make note of it and track the data appropriately for the shifts. But no major change in what we burned.
So Scott, do you find that pet coke is more abrasive or less abrasive than coal?
You know, from my experience, I believe it's less abrasive. It seems, you know, obviously it's a coked out byproduct from the crude oil process. It offers a just a less abrasive ash in general. And the flow what we found are the flow characteristics when we're higher in pet coke, less scaling, less buildup. So yeah, it's a more forgiving fuel, if you will, on the back end.
Okay.
So again, that when Dynergy showed us an example of the insert after over a year of service, and it was still ready to be used. It was very, very convincing.
All right, but before we got to that point, though, we at Lechler had a lot of testing that we had to do for JEA to convince them accordingly. What you see here are the spray tests that we ran in our lab. On the left is the Lechler cluster head nozzle, and on the right is the incumbent nozzle. What we're doing here is using a phase Doppler particle analyzer, for which there are plenty of neat pictures. But we basically will go through a spray cone. The lasers are basically bouncing off of the droplets, determining their size, and we'll measure not only one plane, but there will be a certain range that will run these lasers through to get not just the one point in time, but actually a full characterization of the cone and of the spray. Now, what we found, and I did try to clean up these slides a little bit, but I did obscure the competitor name, and they are now named Incumbent at the time. But what we did, we ran the test nozzles, and we're looking at basically the two major particle size distributions that we look at, and these are all averages, of course. So we're looking at the solder mean diameter comparison. And for the D32, which is most of the distribution, you're seeing a 12% smaller SMD for the incumbent nozzle versus the Lechler nozzle. We were pretty pleased with that. We didn't think that it was that much, that big of an impact. We were expecting to see probably twice that, but this was good. This was in the order of right direction. Now this was all done before they purchased the nozzles though and installed them, which was of course the true test of the material. Also looking at a little bit larger distribution in the D90, what we've seen here is that we're actually significantly more smaller in both sets of conditions than the incumbent was. Now, why does that matter? In general, smaller droplet size gives you more surface area because you have smaller droplets. The more surface area gives you better reaction, better capture rates, and it keeps you in a very uniform cone situation so that you don't have very large droplets at the onset and very, very fine aromatic or aerosol type droplets in the lower portion of the cone. The cone is usually has very good integrity throughout the spray area.
And
Hey,
Stewart,
yes.
there's a question from the audience, and I wonder if you can address that. So the question was, do you have a shared air or purge air around the optimizers in your system?
We do not. We call that barrier air, where we have the tube inside or the nozzle inside a tube, a protective tube for which we blow low pressure, low volume blower air through to keep the lance cool and also cool the head and keep the buildup off the head. But in this particular application, no, we did not have any kind of barrier air or cleaning assist from any of the air sources.
And thanks, Stuart. This is Mitch as well. Like to also ensure that we sometimes ask questions about the fundamentals related to these processes for new people entering the industry. So one of the questions I had is just in general, high level, what is the most important aspect to evaluate for particle size distribution from the nozzles? Is it D90? Is it mean diameter? I guess in other words, what kind of questions should end users be asking about droplet particle size distribution to ensure they are getting the appropriate nozzle? Can you speak to that a little bit too? And Scott, chime in as well from an end user's perspective.
Certainly. Droplet size is most people would say, well, droplet size is the most important thing that you have to look at. That's not necessarily true because it's really more about the distribution of the droplet size. When we say something like 100 micron droplet size, that's the mean of a pretty large distribution. We also have indications of a skew distribution or others, or other characteristics. So really the most important thing is, are you getting coverage in the vessel? Are you capturing everything that you need to without impinging upon the sides of the vessel, which could cause, because of the pressure that we're running the fluid, could cause cutting or scarring inside that inside the vessel, which could be another place for buildup and things like that. We try to take into account the overall situation a customer has, not only the application, in this case, a dry spray dry absorber, but in this case, we knew they were particularly concerned about cost, particularly at this time, compressed air, because they were running a lot of compressed air through here. So when we first set this up, we said, well, since your pain point is compressed air, let's monitor that. And in our designs, we purposely looked at how to minimize the compressed air to mitigate those costs. So long story short, there isn't one silver bullet. Lechler likes to take a very comprehensive view. We'll ask you for very rudimentary data, including flue gas volume and rate, temperature drop you want to affect, or in this case, how much capture you need to accomplish with this system. So again, there's no one thing. It's really a comprehensive analysis, and each application we run into is different. Mitch?
Very good. That was excellent. You took the words right out of Scott's mouth. So there you go.
Oh,
Covered it all, so.
No, it's all good. Keep going. That was perfect. Thanks, guys.
okay. So we at Lechler were very happy that we were smaller in size, but again, there's a lot more to it than just droplet size. So Scott, I'll let you go over the results and comment
Right.
on what we're looking at here.
Okay, so overall, when we switched to the Lechler cluster heads, immediately it's the savings, as the bullet point shows. We went from at least 10.5 hours per week, upwards of 14, to an average of 3 hours per week. Basically we went from cleaning all 16 nozzles per unit every day to 14-day cleaning cycle, which is tremendous savings. Allows the guys to focus on other things, of course. Not to mention the wet bottoms, which we have not had since we procured the Lechler cluster heads. So we're avoiding the man hours, a whole crew out there rotting, potential loss of megawatts for, I'm not sure, when did we purchase these?
I think it was 2016, 2017.
Oh, wow. See, so not a wet bottom since, knock on wood. Our increased SO2 capture rate. So of course we had a certain amount of performance with the incumbents. Our capture rates increased greatly, which saves us that additional, on average, minimum 1 ton of limestone per hour. I've actually found out that the new cost per hour or per ton of limestone is $53 per ton. So at the bare minimum low load situation, we're saving $53 an hour additional due to the Lechler performance. And of course, the air compressor that was eliminated is minimum $30,000 a year, depending on the units and their how much they're running, can be as high as 150,000. So of course that's a fluid situation, but yeah, payback was very quick. Performance continues. Overall, just great product for us. Worked in our application. Wonderful.
Thank you, Scott. I just want to point out that their capital payback was about 3 or 4 months. And if you compare that with the 90-day trial, these things are basically paid back or paid off before they actually made a payment. So I think that's a pretty good selling point. We'll prove it to you, and
Right.
you don't have to pay for it. No, that's not really what I'm saying. But boss, if you're on the line, I was just kidding. Anyway, so it was an excellent project. It was with a power company that was very conservative, and that gave me some frustration, but I got over it. But we were really focusing on the maintenance savings and the air consumption savings, and that would have brought us in about 50,000 a year, which over time would have been, you know, a little bit longer payback, 2-3 years kind of thing, with a capital payback of 3 to 4 months. They were so delighted. They turned around and bought the nozzles for their second unit, which we installed the year afterwards. So I would, Scott, correct me if I'm wrong, those are still running as well, running well?
Absolutely. Yeah. Yeah. We're not having any issues with them. You know, any time an issue might come up, it's typically after the unit's been on an economy outage and we've had some condensation in the atomizing air line, and we get an initial upset of debris, which is typically some surface rust. Once we get that through our cyclone separator. But yeah, performance of the Lechlers is, knock on wood, bulletproof at this point. And I hope it stays that way.
It should.
And
Knock on
Scott,
wood.
Yes, sir.
Scott and Stewart, so we have 2 questions from the audience, and I want to, if you address them. Scott, the first question is, when did you make the change to the Lechler nozzle, or what is the duration of your use of the Lechler nozzle?
So we made the change. I think we started looking into it around 2015. Somebody mentioned to me that there was some other products out there, and they had a reference name, and that led to another contact, which ultimately resulted in Dynegy giving us a visit. So through continued pursuit and investigation and, you know, troubleshooting, initially I started troubleshooting with the TurboTax to see if I could initially decrease the air with those. And unfortunately, we couldn't do that. So then I continued looking into the Lechlers, and that's when I ultimately met Stewart. And then we started some tests with his product, which was very convincing. And I led those tests, and they, involved airflow, exactly what we could reduce it to and have them perform. Of course, I used Dynergy as a reference since they had them for a couple of years prior to us. To the maintenance needs, overall performance, so that's when we made that transition around 2017.
Have you seen a similar durability as a domaining experience?
I'm sorry?
So talking about the duration, have you seen a similar durability as a domaining experience?
Have you seen similar durability as Dominion's experience?
Yes. So even our unit 2, which is typically has more economy outage or off time than unit 1. Both of them, the durability is fabulous. We've not had any issues with the tungsten carbide inserts. We have only had one where the slurry tube female receiver in the cluster head was actually, I think it was a fault of ours that our gentleman left out a gasket and it caused a little washing, but that was our fault. Unfortunately, fortunately, it did not cause any permanent damage to the cluster head, as the insert can be replaced. So it was replaced. But performance-wise, we have not seen a reduction. We're still on a 14-day cleaning cycle. Our capture rate remains virtually the same. And I can only assume that if our performance or SO2 capture rate starts to decline, then we'll have to look at potential replacement of those tungsten carbide inserts and any other potential wear point inside the cluster head. But thus far, we haven't seen any of that.
Excellent. Well, we have about 7 minutes left, and we still are getting questions from the audience, so that's fantastic. Another question here. Any difference in pressure drop from the incumbent nozzle versus the Lechler nozzles? Can you comment on that at all, Scott?
What do they mean by pressure drop?
In the vessel? Or
in the vessel.
I mean, is that what the question asking?
That's a good question.
Right.
Yeah, no clarification there, just any difference in pressure drop from the incumbent nozzle versus the Lechler nozzle. So maybe I don't understand, that could be interpreted as the process or the actual nozzle itself, but is there any way that you could maybe address both just in case?
Trying to think back to the testing days. So
Without, of course, giving away the secret sauce, Stewart, that not, you know what I mean here, okay?
Oh, am I supposed to answer that? I'll let Scott answer it because
I would say on my end, we were a little more less concerned with the engineering dynamics of it. We reduced the atomizing air, of course, from 290 CFM to 230 to 35 on average, 235. So as far as pressure drops, we could say the SDA vessel, we're spraying a slightly less volume and still attaining the same or better actually capture rate with less volume of slurry on average.
Gotcha.
So Sure, could that potentially equate to a slight pressure drop in the SDA vessel itself, or less pressure? Not necessarily a drop, but that's potentially there. Um, so,
Okay.
Sounds like a no.
it's hard to say. Yeah, I would say no.
Well, okay. We'll go to the next one too from William Ciro. William's asking, good morning. Did you see any issues with mercury capture with activated carbon? Anything you can comment on there?
Well, actually, we do have a activated carbon system, injection system. We only have to use that if our fuel dictates it. Most often it does not, but we have purchased some fuel within the last year and a half that dictated we inject some activated carbon. It didn't seem to have any effect on the SDA and the performance. And most often we don't need activated carbon due to the size of our bag house system, which was originally oversized. So it would capture mercury to an astounding level. We're always below the EPA regulated standards, unless we buy that certain fuel, coal that.
Okay, we got a comment from Kevin Redinger. Says maybe the question is the air pressure the same for both nozzles? And as I recall, correct me if I'm wrong, Scott, the Lechler nozzles were considerably lower in pressure and volume.
Right, exactly. With the lower volume came lower pressure. One reason with the TurboTax that we had such a high volume air is we were trying to extend our cleaning time, and just trying to blow them clean, which was to no avail. So yeah, lower pressure with the lower air volume, of course.
Excellent. And then I was going to ask one more question too. So going back to the beginning of the presentation, have the Lechler nozzles addressed or improved the issues that you've seen with the previous nozzles, as far as the plugging and all that good stuff, the stuff you showed on next slide, Stewart. Keep going. I'm sorry. The one with
That
the
one?
pictures. Yeah, that one. Has this improved?
I will say that I can only assume it's due to their nozzle tip design that the we don't get that heavy build up directly on the head. It will be beard somewhat around the nozzle tips themselves, but it doesn't interfere with the performance. Like I said, depending on how we're spraying the boiler conditions, of course, from 13 to 15 days, you've got to, or at least we have to clean the Lechler cluster heads, where the buildup on the incumbent previous nozzle cluster heads were daily. It was overwhelming. Build
Well,
up
Scott also came up with a very innovative cleaning concept, and Lechler helped him design a unit where it's basically a box and all these cluster heads were on a quick disconnect. So he would take a cluster head, put it in the box, and then we would actually run acetic acid, dilute acetic acid through there, and that all that motion and all that energy cleans these things like you wouldn't believe.
That's a good point. It's just a wash box with the cam lock adapters. We place 4 heads on there, flip the switch on the chemical pump, which has a preset 3-hour timer, and the guys flip down the plexiglass safety lid, and they walk away and then come back and swap the heads out. So very good.
It's a lot better using acetic acid than muriatic acid, I think you were using before.
Oh, yeah, and part of that was, we knew it was an aggressive acid to use, but since the cleaning was daily, we had to speed up the cleaning process. So, very true.
Well, perfect. Well, I think, I want to thank you guys. That was a really good presentation. We got a lot of questions, so I appreciate the engagement from the audience. We're going to transition. So thank you, Stewart and Scott, for that presentation. That was very helpful. And before we get to the second half of our webinar, ladies and gentlemen, we're going to do another commercial break. Thank more of our sponsors. So I'm going to share my screen and give some kudos to our other important sponsors. So hold on. So you should see a slide for Redicam. Here's another one of our loyal sponsors. Redicam provides an extended range of equipment for flue gas treatment and air pollution control systems throughout many industries. They serve end users with technologies to meet stringent emission reduction needs in a cost-effective manner. They have wealth of experience through over 4 decades of operational experience. They're a reliable partner, whether it's a greenfield site, retrofit solution to achieve your air pollution control objectives. And Salvatore Gallo is also a DSUA advisor with us who volunteers his time to support current activities. So we want to thank him as well. Next sponsor we want to thank, National Filter Media. They are also one of the raffle sponsors that I mentioned at the top of the webinar. NFM takes pride to be one of the world's oldest and largest provider of air pollution control and liquid filtration products. Successful in adhering to the same business principles they've been practicing since founded in 1906. So pre-Titanic days, guys. So they've been around a long time. They believe in building partnerships with end users and earning the business on a daily basis. And while filtration technology has changed since 1906, their commitment and principles have not. So thank you very much, NFM, for being a sponsor for DSUA. Next is Lechler. You may have heard of them. They just presented with Scott. Lechler has over 140 years of experience in designing and manufacturing spray solutions for air quality control systems. They have a wide range of nozzles, nozzle lances, valve stands, mist eliminators, etc., to provide solutions for gas cooling, purification, denitrification, or desulfurization applications. They advise customers with custom solutions to meet their needs to achieve compliance with stringent emission requirements. They're experts, understand spray technologies, and share their expertise and solutions through partnerships with end users. And also Stewart McKenzie, who obviously just presented, is currently a DSUA advisor who has been volunteering his time to support current activities. So we'd also like to give a special shout out to Stewart as well. And then lastly, last but certainly not least, Gecko Robotics. Those of you that were on the last webinar got a chance to get familiar with them as well. They have a revolutionary robotic technology for industrial infrastructure inspections. That's a mouthful. They're a really cool product. One of their main products is wall climbing robots and inspection teams that perform NDT inspections for global clientele. The robotic technology enables execution of routine inspections with comprehensive data collection. We're talking millions of data points at high speeds that are collected safely in hazardous environments. Recent years, they've been very supportive of DSUA through board positions, as well as helping facilitate the platform for the current webinar. So thank you very much to Sam Link for helping us out, helping me out, making sure this is running as smoothly as possible. And then if you're interested in learning more, to check out the February webinar that Michael Paul Jenkins hosted. So big shout out to Gecko Robotics as well. So with that, I will turn it back over to our moderator, Dr. Liu, to introduce our next speaker, Curt Biehn. Go ahead, Guisu.
Thank you, Mitch. So our next speaker is Curt Biehn. So Curt is a technical director for Mississippi Lime Company. He has been with Mississippi Lime since 2008. focusing on air pollution control in dry scrubber and dry solvent injection systems. Curt has worked with the industry optimizing hydrated lime DSI, including conveying injection prior to the air preheater and the development of enhanced hydrated limes. I believe that's the topic he's going to present. Curt also has worked with dry scrubber users to evaluate enhanced hydrated lime variants for overall cost benefits. Curt has a BS degree in chemistry from SIU and MS in organic chemistry from the Ohio State University. Prior to joining Mississippi Lime, Curt has worked in the specialty chemical industry in several roles, including technical services, operations, quality management, and applications development. Now I give time to Curt and let him to talk about what their experience on the optimizing the systems. Curt.
Thank you, Guisu, and thank you all for joining us today. In the latter part of 2020 at these webinars, we had a couple of presenters mention the benefits of enhanced hydrated limes. It wasn't necessarily the full focus of their presentation, but so they didn't go into great depth on it. And with that in mind, and the fact that there's also been over the past few years a lawsuit that sort of one of the crux of the issues was the definition of enhanced hydrates. I suggested or asked Jerry if it would be prudent for me to kind of to cover that and cover some fundamentals of enhanced hydrates today. So I want to talk a little bit about the background on air pollution control using hydrated lime. Get into the challenges of defining enhanced hydrates and show you some examples of benefits from their use. And then also at the end, talk about influencers on enhanced hydrate performance, how to maximize your benefits from it, or how to best quantify versus standard hydrate. If just to get everybody on the same page, hydrated lime is calcium hydroxide. It's produced from solid quicklime, calcium oxide, and water in a hydrator. It's the end product is a powder, is a fine powder. Standard hydrated lime prior to probably 2007, there are and were wide varieties of qualities, and for air pollution control, it probably wasn't all that specialized. We did see in slaked quicklime, which were the hydrated lime slurry applications, that there was some differentiation with particle size and so forth of the hydrates in performance, but nothing significant. About 2007 to about 2013, saw the advancement of flue gas treatment grade hydrated lime. And these versions had consistent quality markers for surface area and purity. And they were really the workhorse of the DSI industry for SO3 mitigation that began in about that same period. There was some acceptance for circulating dry scrubbers using purchase hydrate versus on-site hydration. In the past 6 or 7 years, we've seen a big growth of enhanced hydrates. These versions, different from the prior two, are generally proprietary or IP protected by the supplier. And these products give higher performance when in DSI applications that go kind of beyond environmental control, where you get air preheater benefits. If you couple it with activated carbon injection for mercury, back in 2015 for HCl mats requirements. There are preferential options depending on the pollutant you're trying to mitigate. And we have seen that usually enhanced hydrates are the best economics for the end user. Okay. Trying to simplify it as much as possible, when we use hydrate for control of acidic gases, you've got a flue gas pathway that comes into a baghouse or a particulate collection. And at some point in that pathway, hydrated lime will be injected. Usually hydrate has a D50 of about 2 to 8 microns. And it's injected into flue gas where the gas particles are much smaller than hydrated lime. So the relative difference is significant. And the period between where the hydrate's injected and the particulate collection is where we'll get in-flight capture. And the goal there is to maximize the collisions of the hydrate with the acidic gases in the flue gas. And then once those particles reach the bag house or the ESP, mostly in the bag house, so we would see kind of fixed bed removal. And that tends to be more of a thermodynamic concept in the bag house, where the rates of reaction, the relative rates of reaction will dictate performance. We've got some graphs there. This is from a presentation of Nalco Mobitech several years ago, where we see that SO3 is much faster reacting than SO2 and then the halogenated acids. The one thing that you have to consider too is concentration in this effect, whereas SO2 will have typically a much higher concentration in flue gas as opposed to the other three, SO3 or HCl. While we're in flight, the capture is generally very fast at the surface of the particle, and that kind of drives the performance, whereas absorption into the core for for neutralization is relatively slow.
Hey, Curt, we have a question from the audience, and I wonder if you can address that. So the question was the conditions for using the enhanced hydrated lime in SO2 control. So the conditions like temperature, humidity, or like the calcium by sulfur ratio.
We will eventually get to some of that, maybe not as specific as we need, and if we do, we can probably ask that at the end. I tried to put some things in after I saw that, so.
Okay.
Yep.
We'll stay tuned. We'll stay tuned, Curt.
As far as in-flight versus overall capture, the majority of the pollutant removal and DSI is with in-flight capture. We've got an example here from some pilot testing that we did at Babcock and Wilcox several years ago, and we see on the dashed line was the in-flight capture with the respective hydrates, and we see that the red, which is an enhanced hydrate, was much higher in flight than the FGT grade, and then the overall capture was slightly higher, but the majority was with the in-flight capture, and that's been supported by a lot of other. I know I've asked questions at conferences, and what people have seen on their tests is that most of the capture comes in flight, well over 50%. It's important to note that we think our stuff is good, but our particles aren't smart. If the gas is in the way, it's going to react with it. Remember, they're relatively large compared to the particles. So if you have a stratified flow and there isn't much SO3, and that's what you're trying to get, it's going to react. The hydrate will react with whatever's in there, whether it's SO2, CO2, HCl, and so forth. So that's why it's key to have good, consistent coverage of the flue gas. Why would this be important for a dry scrubber? Most dry scrubbers have some type of reaction zone prior to particulate collection. And what we believe is that the fresh sorbent is most active in that zone, and any hydrate that you recirculate has severely diminished activity.
So just to clarify there too, Curt, and I'm thinking about the new folks in the industry. So that slide is, I know that there is I'm not going to call it a myth, but a hypothesis that a significant portion of the capture, like for example, if you have a bag house, happens on the bags and not in flight. You're saying that the data does not support that hypothesis. Is that correct?
Well, I mean, a bag house will correct a lot of errors. I think if you're looking for very, very high rates of removal at the outlet or at your stack. A bag house doesn't hurt. When you get into more challenging aspects, SO2 removal with hydrate, the bag house is going to help.
Gotcha.
But if you imagine the circuitous pathway that hydrate would take from the injection point to the bag house, while it's also being exposed to SO2 and CO2 and other species, it's going to react with something.
I
And so
appreciate it. Yep.
that's why I think, we feel it's key to, to the coverage and reactivity are key. I'm not saying you won't get anything on the bag house, but you've got to kind of broaden your thinking beyond just the fixed bed type removal.
Thank you. Perfect.
Air pollution control applications, dry sorbent injection. Most of these applications are for SO3. In the, I guess we can refer to them as the old days now. Post air heater injection was simply to meet air regulatory requirements, and we were injecting after the air heater, and in some cases even after the ESP. We advanced the process to where we did pre-air preheater injection to maintain cleanliness in the air heater and gain other operational benefits while still getting the environmental control that was required. And currently the focus is on pre-SCR injection to allow the unit to gain efficiency at low load operations, because coal-fired boilers are cycling substantially more than they were designed for, and this allows a cost savings, and when we can go, drop minimum megawatts, sizable amounts, 20, 50 or so megawatts. For dry scrubbing, it does use a little bit of added water, as we heard about with spray nozzles and so forth, for wetting the hydrate particles, and the wetting makes SO2 removal much more efficient. In circulating dry scrubbers, you have the flue gas enters, and you've got the reaction zone, which does some removal. It's got the benefit of a water spray, and then the cycling from the bag house. NID scrubbers, they will generally produce hydrate at the point of contact, or near the point of contact and injection into the duct work, but there is a hydrate component there. And then spray dry absorbers, which are generally produce it's generally a slurry produced from quicklime, although I know of at least one application where they, for utility, where they use purchase hydrate, and there are probably some small industrials that use purchase hydrate for spray dry absorber applications, but that's more of a sprayed solution.
Good. I have a quick question. So this slide, you talked about the applications in a DSI and in a dry scrubber. So what is the most important, the line properties in the dry scrubbing systems in compared to the DSI?
Guisu, I think we may have that covered in a little bit. Maybe a couple slides from now, I'll get into that.
Okay.
Okay. So the potential benefits, I mean, you can certainly, the main goal is to reduce the emissions of acidic species, or maintain those existing emission levels while lowering your annual delivered sorbent costs. If you feed, excuse me, if you feed a lower amount of hydrate, you will also have lower ash generated, and especially with dry scrubbers, that can be a substantial savings. Higher performing hydrates will give you flexibility if you want to use higher fuel sources, higher sulfur fuel sources, or higher chloride sources, or if you're going to do some changes to your SCR operations to maximize NOx reduction. If you're getting less shipments in your plant, then you're going to have less truck traffic, and every time you hook and unhook a truck, to deliver product, that's a potential safety exposure, and you would take that out of play, or you would minimize that. If you're circulating dry scrubber using an on-site hydrator, you can eliminate that as a potential maintenance headache. You can also eliminate the parasitic power, and there's a definite cost per ton to run a hydrator on site. You can take that away with using purchased high-grade hydrate. And then finally, you can increase the number of days of sorbent storage on site. If you know you can fit, I don't know, 5,000 tons in your silo, and you can get by. You certainly have more effective tons with the hydrate, because your feed rates will be less. So what makes a hydrated line enhanced? And in my view, it's that the lime supplier has modified our manufacturing process to consistently produce a hydrate that has more active sites for neutralization of acids. And if we think in terms of effective surface area, and there's a textbook on this, probably 30, 40 years old, from J.A.H. Oates, and I'm going to defer to him. Those effective surface area drivers are specific surface area, total volume and size of the pores, the particle size, and the degree of agglomeration. So what you're trying to do is kind of juice up your reaction sites for that in-flight capture and that capture on the baghouse. Right now, our estimates are that 60 to 80% of hydrated limes used in air pollution control market are enhanced hydrates. So many people have converted. So what makes an enhanced versus a standard grade? And this is a very general comparison using those classifications. And I put it here, and I'm sure that other people in the lime industry, I'm happy to discuss them when we all get back together. But my feeling is that the hydrate should meet at least two of these properties to be considered enhanced. So a BET surface area may have a typical surface area of 18 for hydrate, whereas enhanced hydrate lime will be greater than that. Pore volumes on typical is about 0.09, and that would be higher for enhanced hydrates. D50 particle size of about 5 micron. Those would be smaller to make smaller particles more to meet the definition. And then the D90 kind of is an agglomeration definer. You know, those may be around 15 or more. More enhanced hydrate, it's smaller. Now the caveats are that enhanced hydrates are patented or proprietary technology. So comparing suppliers is not simple. The two suppliers that offer this have chosen different pathways. So if you're an end user and we are probably going to give you some headaches, because we're going to talk about why ours is better and what benefits it has versus the others. It's not going to be a drop-in comparison. And by that token, those specifications are good, but the proof of performance comes in plant evaluations. And that I think is key to make sure that you've evaluated the enhanced hydrate fairly. As far as ways to do it, ways to screen the product, one good way is, and we kind of refer to that back with the B&W test, but also something we've done in-house, and I think as others have the capability of using some type of entrained flow reactor where you generate simulated flue gas with SO2 in this case and some heated air, put a measured amount of hydrate in, and then measure the SO2 drop from baseline with a gas analyzer. And that allows you to do this comparison under control conditions and sort of work to define what your expected performance would be in the field. So this chart shows a performance comparison in pilot plant studies. And the and it's intended to show the benefits of enhanced hydrate based on meeting the 4 criteria of oats, which I'll denote with these little pie charts that show up. Now, this chart here is for SO2 removal. We've got SO2 as a percent on the y-axis and the increasing calcium to sulfur molar ratio on the x-axis. This curve would be different for SO3 and HCl, and SO3, it would be different for HCl. So I don't want you to think that this applies to each one of those. So on this one, the black line in this case is a sample of a utility on-site hydrated lime, where they took quicklime and made hydrate, and then we were given a sample and evaluated it in this application. So its SO2 removal performance in this application in our pilot plant screening was not spectacular. The red line shows an FGT hydrate performance in this in-train flow reactor, and it's got one property that meets the oats classification, and it's better than the on-site hydrator, but it's again not spectacular. The yellow line is an enhanced hydrate that meets 2 of the criteria, and it shows a substantial improvement over the FGT and the utility. And we see growing improvements as we add classifications. The blue line, we've met all 4 classifications and see very good SO2 removal. And then the purple, which has a couple of these classifications supersized, it gave very good performance in the in-train flow reactor. The 2 examples of how you can use these. One is, say we said, well, at a calcium to sulfur molar ratio of 2, we see higher performance at equivalent feed. So a utility on-site hydrate may be 20% removal, whereas the enhanced hydrated lime 3 would be about 75% removal. That's a big jump. The other way to use it would be if you've got reduced usage for equivalent removal rate. So if we're using enhanced hydrate 1, and say it's about 2.5 stoic ratio to get 60% removal, well, enhanced hydrate 3, we've got maybe 30%, 40% less to get those same removal rates. So those are guidelines that help us predict what performance could be out in a full-scale demonstration.
Hey, Curt, we have a question from our audience. I think this slide probably can address that. So the question is, if the CDA recirculates or recycle the residual from the absorber, will you see the NSR of the standard hydrate line equal to the NSR of the enhanced hydrate line?
Generally, no. Generally, no. The recirculation, they may get compressed a little bit, but it kind of goes to the way the reactors are designed. I think you really get diminishing return. If you imagine a hydrate particle, the first time it passes through that the CDS system, through the reaction zone on the bag house, that's at its maximum performance level, and it's going to grab as much as it can. By the time it's sat on a bag house, it's been exposed to SO2, CO2, and so it probably will be diminished when it gets circulated back through that reaction zone. So I think our theory is that you have to grab as much as you can grab when it's fresh is the higher performance.
Thank you, Curt. Appreciate that.
So here's some examples of using circulating dry scrubbers with enhanced hydrates. This first one, it's a comparison of enhanced hydrates to purchase FGT hydrate. And these were averages conducted over multiple weeks. And what we saw overall, though, there's about 25 to 30% less hydrate used when they went with HCl. One thing to note on that is the difference in the performance at different loads. And so at high loads, they were fairly squished together, if you will. at low load, there was a huge difference in the red enhanced hydrate performance. Now, the site did convert to enhanced hydrate due to significant cost savings and ash disposal benefits, and they've continued to use enhanced hydrates for well over 4 years now. The second example was versus an on-site hydrated line. Now, this is one where we had actually done some work with them and helped optimize their hydrator. And so it's a very good hydrate. And it's also fed by a volumetric feeder. These were averages over multiple weeks of performance. They used about 20 to 25% less hydrate with HCl. They did not have significant ash disposal costs. And because of some, the performance benefits were good, but not quite enough to overcome the freight and the low ash disposal costs. So they stuck with what they had. This one is a comparison versus purchase hydrate, and this company conducted multiple evaluations of different enhanced types, and they saw significantly less hydrate with enhanced variants, with the EHL variants, along with the disposal savings and some operational benefits, and they have used enhanced hydrates for several years to their benefits.
Curt, I had a question. In general, can you comment on how critical the specific CDS design or operation is in regards to the benefits an end user can absorb or obtain with enhanced hydrate?
Well, I know Tony Licata's on this, so he'll probably, and Kevin Redinger, they'll probably tell me afterwards that there are differences. I think there's probably some differences. We've seen benefits in multiple types of multiple brands of dry scrubbers, if you will. There aren't that many out there as there would be, Mitch, like you'd be familiar with DSI systems. You don't have many, we just haven't seen and tested enough to see if there are subtle differences in them.
Gotcha.
Okay. This is a cement plant evaluation for DSI SO2 control, and we see standard hydrate, but they've got a certain kiln feed and then a hydrate tons per hour, and then they had to meet a stack SO2. So we went to enhanced hydrate. We saw lower hydrate use and cut the stack emissions in half. When we tried a different hydrate, we got even better efficiency with the hydrate and dropped the stack emissions. And if you targeted the stack emissions for about the same as the standard hydrate, you would get significantly better utilization. And this customer did convert to enhanced hydrates. So just an example on like ash and truck savings, if you have an enhanced hydrate that's about 60% less, 60% of what your FGT amount is, that's for a 10,000 ton a year plant, that's, you take it down to 6,000, that's a lot less trucks, and at $30 a ton ash disposal, well over 200 grand in this example case for an ash savings. So we get asked this sometimes, or we get told our enhanced hydrate doesn't work like you said it would. And I wanted to, and it's come, during a demonstration or questions, and kind of go into some things to do and to look at. There are no two plants or conveying systems that are identical. And we've seen that conveying and distribution system issues lead to deviations. And when we run demonstrations, it really needs to be on steady state processes. This is one example where somebody wanted to evaluate for mats, and they started with, and this is for HCl removal. At the beginning of the trial, they had 2 lances per duct, and on the triangles there, they had good performance, but really wasn't doing the job. And they changed to 4 lances per duct, and they achieved that. So they got more injection points. There are several types of injection grid upgrades, whether it's tied to the lance or the injection system, or whether it's in the actual position in the flue gas and in the ductwork of the flue gas. And the intent is to better disperse the hydrate cloud. And this from Chad Donner of Duke shows what he encountered going from standard lances and standard hydrate, which are the green, blue, and red lines. And then as you move to the left, upgraded lances got him to where that purple line is, where he had less hydrate use. And then finally coupling the enhanced hydrate with the upgraded lances got him even better reduction. So that mixing does help dispersion. This is a very recent example of an injection grid optimization that we did, and this is for hydrate upstream of the air heater for DSI. And this was a grid that was configured based on a CFD model with lances of varying depths. And we measured performance at the inboard and at 2 points, the outside and the inside of the ductwork at the air heater inlet, using a Biehn probe to monitor condensable formation. And we measured it at 4 total depths, and we measured it with hydrate on and off. And one of these traverses, I guess per duct, would take about a day. And what we saw, comparing enhanced hydrate on versus off, is in this chart here. This is enhanced hydrate off, and you've got A duct on the left, B on the right, and those values are condensable formation, and lower is better. Lower is less SO3, and anything with above about a 260 indicates increasing presence of sulfuric acid. So we see in this case that there is some bias to the south wall on the A duct. We see a darker red on the south wall, and we do see a little bit more acid on the B duct side. We don't have, is indicated by the lack of the yellow. With hydrate on and measuring the condensables through the traverse, we see the outboard sides have very little condensables, whereas the inboard sides have a relatively high amount of condensables, which indicates a likelihood of an inefficient split in enhanced hydrate flow and conveying system. And we actually, this was supported by some of the ash testing that was done downstream, where we were able to identify, it matched up that we were getting inefficient split, where too much hydrate was going to the outside. So what we figured is that we needed to have the utility make modifications to the injection grid and the splitting. And they've done that, and they actually did see significant benefits, or we did see these sort of inboard issues corrected. So in a nutshell, if you want to,
Could it just remind you, we have 3 minutes.
I'm going as fast as I can, man. I gotta, let's see, we can add injection points. We can use mechanical means to disperse better, and we can correct distribution errors. For SO2 removal, I think many of us have seen this slide in one form or another in presentations over the years, and that's a historical number showing optimum temperature for SO2 removal. Now, those tests were probably done in the 70s, and those were using standard hydrate. And so we've always kind of respect that data, but a lot has changed since that time. So with large scale utilities, DSI, we know that over 50% SO2 removal is easily attainable with enhanced hydrates, and really figured that continued advancement with enhanced and injection grid efficiency, I think you can go over 70, probably over 80. There just has to be a reason to move there. With circulating dry scrubbers, some of the challenges you have to deal with are longer proof of concepts. We've got recycled ash, so you can't just do a day for this test. It's got to be over a week period. You've got to have inlet SO2 tracking. A lot of circulating dry scrubbers will use volumetric feeders, and you have to be aware of the properties differences between the standard hydrate and the enhanced hydrates, so you understand how much you're feeding, and then how you're going to deal with any startup or shutdown or upset conditions during evaluation, because hydrate use at those points is relatively inefficient. So in summary, hydrate performance in any air pollution control system is a function of in-flight and particulate collection capture. enhanced hydrates are well accepted and used in a majority of utility industrial applications, although defining them can be a challenge due to the individual supplier's proprietary technology. And that's why it's always best to test and evaluate. And then finally, if you're going to do those evaluations, you should understand your flue gas and your hydrate delivery system to help maximize the value from your enhanced hydrate. And that hit my mark. Guisu?
Very
Thank you.
good. Excellent.
Just two quick questions if you can address. So the first question is the talking about the milling of the lime. So is that the final particle size can boost the surface area and also the performance?
I'm sorry, what was that?
The finer particle size, would that boost the performance? Small particle size.
I think that is our position. Yes.
The second quick question is the difference between different scrubbing equipment between a DSI and a CDS. Is that due to the solvent dispersion, the distribution?
I'm not clear. The sort. Do you mean the performance? Well, I'm not sure I understand the question.
Yes, so the question was, is the performance related to the distribution of the solvent in the DSI versus the CDS?
So in other words, the differences in performance related to scrubbing equipment. So there's a difference in efficiency from DSI to CDS to SDA. I think it's more just a clarifying. Is that specifically related to the sorbent distribution or efficiency in those technologies, or what causes that difference in performance? Is I think the question.
Well, it has to do probably with, I think with SO2, with CDS or any type of scrubbing application, you've got an element of moisture. I've added moisture with spray nozzles or with solutions, whether you're doing a lime slurry, and I think that can accelerate removal of and that's what helps them get the 90-95% plus removal of SO2 in those types of scrubbers. In DSI, you don't have that help, so you're kind of, for lack of better, the hydrate's kind of on its own there, and at that point you've really got to rely on how well you can distribute and cover the flue gas with this. You're essentially blowing dust in the ductwork, and how well you can cover that. Like in CDS, it's the hydrate comes in, in a throat in one area, and it's not kind of dispersed throughout that reaction zone. So you've got a very, very concentrated at that point when the flue gas hits it, plus the moisture. Whereas in DSI, you've got to spread that out over however wide your duct is, 30, 40 foot wide, with a 2-inch, several 2-inch lances.
God, thank you, Curt. And then I think we're going to have one more question. I know we're not going to be able to get to all of our questions. We'll try to follow up accordingly for those that we didn't get to. But the last question, Curt, is from Kevin Redinger. He asked, does enhanced hydrated lime require any changes to the lime storage silo or transport system? Or can we utilize our existing equipment essentially as is? Can you comment on that?
It should, especially for a CDS system, it should not require any changes whatsoever, because most of those that I've dealt with, it's a rotary feeder onto an air slide, and they have just pretty much dropped it in. So no, you should not require much change or any change with a CDS. With a DSI, I mean, our materials is different from our competitors' material, and I think people know enough to tune around that, and they can make it work in DS. They can make either one of them work in DSI. And if somebody tells you they can't, we generally both push back.
Gotcha. Well, I appreciate that, Curt. So I think, again, yeah, just appreciate your time, Curt, and talking about some enhanced hydro line. With that being said, we'll kind of go to the wrap up of the webinar. It would not be a true webinar if we didn't have some technical difficulties, and for some reason I can't access my camera, so you guys are just going to have to hear my voice and attend the next one to see my face again. So again, I just want to thank our speakers. We cannot do this without their valuable content. They're obviously the meat and potatoes of what we're doing here. So thank you to Curt, thank you to Stewart, thank you to Scott for doing that. Also want to thank our moderator, Dr. Lou, who's also a sponsor as well. We want to thank all of our sponsors. As again, like I've mentioned earlier, we're nonprofit, but non-functioning without our sponsors. So they volunteer their time, they volunteer their money, help carry our mission and share knowledge with others in the industry. I want you to stay tuned for the recording of this webinar. Again, it'll go up on YouTube very shortly after the conclusion of it. If you're looking for more content similar to this, you can sign up for a DSUA membership and get access to all of our conference presentations dating back to 2008. So going back to the old days, like Curt mentioned in his presentation. If you have any interest in presenting, we encourage you to please submit us an abstract through the DSUA website. We all have stories to tell that others would find interesting. So the more we can share, the better for everyone. And then also be on the lookout for updates on the April DSUA webinar. So Curt, I want to give a special thank you to you for filling in as my my video my video substitute while my camera's not working. So thank you for that. Appreciate everyone for attending, and I hope you all have a great rest of your week, and we'll see you on the next webinar. Take care.
Thank you.